welcome back to this second morning session in this room. We are going to talk about regolith handling. My name is Philipp Reiss from the Technical University of Munich. I'm the moderator for this session, and to not lose any further time, I would start and introduce our first speaker of the session, Professor Dr. Matthias Sperl from the German Aerospace Center in Cologne. And you have 10 minutes. The floor is yours.
Thank you, Philipp, and thank you to the organizers for putting together such a nice program and the honor to be part of that program. So handling, I think, is a big word. So what we will mostly have in this upcoming session is results from handling in 1/6 gravity, where we had the pleasure of using a lunar parabolic flight to test some of our experiments. And I expect many of you may have been on parabolic flights, or at least know the operations that Novespace has done so beautifully in Bordeaux. And we're all in that new A310. And just to give you a little bit of a recollection, many of you have been on a parabolic flight with 1G. So whenever you fly from point A to point B, you can have an arbitrary number of seconds in 1G. And the more I reduce the time, the lower is your gravity, and the reference point should probably be the 20 seconds, 22 seconds in zero gravity, and if you relax that, you have 24, 25 seconds in lunar gravity. And there's one qualitative difference. If you target zero gravity, any of the noise you experience makes a qualitative error in your experiment, while if you go for point 16, point 14 to point 18 is close enough. So in some sense, the lunar parabolic flight is the truer experience to the lunar gravity than you would have with a zero gravity level. So what did we do? We also advertised a joint drag. So we were expecting many people being interested in the parabolic flight. So we took 3 experiments together, and I will briefly show this one and show the other 2 in more detail. And we occupied some of the real estate on the plane. You have here some straps to not lift off in 1/6 or microgravity. And we have fluidized bed, vibration pumping, and angle of repose, that all 3 of them worked beautifully. We had a relatively large team with a PI from Japan, who was a former member of the group, Masato Adachi, and many people responsible for the individual experiments and helping out to bring things to fruition. So the first experiment you see here is a jointless way of transporting stuff in 1/6 gravity. You see no regolith here, and it's gradually coming up, and this is real time. So this is a way to transport grains without more than just a tube and a vibrating motor. And we put 2 of those realizations in one rack, monitored the results, and we are doing the evaluation right now. The first experiment I show in more detail is the angle of repose, rather the dynamic angle of repose, a standard way of characterizing the flowability of grains. Here you have dry, non-cohesive glass beads. Here you have regular simulants, and for the same conditions, you see that even the cohesion among the particles makes a difference. And for the non-cohesive things, you have an S-curve deviating from the angle of repose, and you have sort of shoveling things to introduce a change in the cohesive regolith material. So we run that with 2 things at the same speed. We have some monitoring cameras controlling. Keeping things simple is always a plus, because the fewer things you have on board, the fewer things can break from one day to the other. And we are operating things in hypergravity, in Earth gravity, to collect a lot of data. And if you go from 1G to the hypergravity phase pulling up, you go to 1/6 gravity and then hypergravity again, you see that there's a visible and drastic change in the angle of repose or in the behavior of the material in and by itself. So we characterize things into 3 qualitative states. Not all the qualitative states identified as identical are in fact identical. We do the more detailed analysis then later. So for the non-cohesive part, you have a nice and well-developed angle of repose for higher rotational velocities going over in that S-shape, and you have what we call a centrifugal shape where no angle or no slope is identifiable anymore. You could also go over to the cohesive case, which has a more rugged way of showing a angle of repose. The angle of repose for cohesion is typically steeper. We have a cascading phase where no angle can readily be detected, and the centrifugal phase is usually very similar. And here is the overall qualitative result. So all the dots are the 100 or 90 plus parabolic trajectories we had. And we have on the y-axis the gravity level, lunar, Earth, and hypergravity for both realizations. And we have sort of the effective acceleration given by the rotation of the drum on the horizontal axis. And you see that we mostly can identify all 3 of those regimes. For future flights, we try to extend things over here and to the left, and we will also have some more things in between that we want to measure to actually test some models in detail. And I move on to the fluidized bed, where we have a nice way that's typically also used for processing. Say you want to flow hydrogen over regolith to extract water and oxygen. And we monitor that both with a laser and a camera. And we find, I'm only showing the camera data today. Let me start all 3 of them. So successively increasing the gravity level means we have a higher driving force for the bubbles going through that. And I'm not showing today the laser scattering that goes deeper into the system, but that is also currently being analyzed. And it looks like a fluid, but it isn't, and it has different hydrodynamic instabilities, and that's what we are interested in to find out what the performance of such a processing unit would be on the moon. Now let me try to go to the full diagram. So since it's not starting, I can explain the diagram again. So again, we have gravity going from bottom to the top, and we have a higher driving force in the pressure difference and the throughput from left to right. And we see very nicely that we have, for high pressure, no visible bubble formation, and the very distinction between an aerated Geldert-like regime for the specialists and the bubbling motion is different and very nicely shifts with gravity. Again, we are doing the details here. That is an early scaling plot, and one of the ideas would be to fill that gap for just testing the models, which would interestingly be Martian gravity. But in general, we have very nice monotonic trends, much more details to be analyzed, and somewhat more gaps to be filled for the next flight. And with that, I wanted to both thank you for attention, show you, and this is not just a montage or a video or AI, it's a real video from a second plane taken following our plane. There's an announcement open by ESA with a deadline, I think, mid of June, to apply for additional lunar parabolic flights. And I hope what I showed you as our preliminary results already gives you a pretty good idea what you can achieve with moderate effort and a decent machinery to clarify some physical boundary conditions and some technical questions for many of the process engineering requests that you would have to operate things on the moon. I have 2 more people that we met on the plane in the subsequent talks, and I'm especially happy that my advice to the ESRIC people to go on a parabolic flight was heated so tremendously well. And I'm very much looking forward to also see their results. Thank you very much.
Thank you very much, Matthias. We have one question, and the microphone is coming to you.
Jerry Sanders, Ezric. So what regolith did you use in a test? I thought I saw JSC2.
No, I think we used EAC1.
Okay.
But I'm not 100% positive about that. Yeah.
Okay, because I know JSC is terrible from a mechanical simulant point of view. So.
Well, in that sense, we don't care what we simulate. We want to have the boundary conditions and understand the modeling of our machinery. Yeah. So what we would rather do is go with a non-simulant glass simulant and tailor the cohesiveness manually by making chemical coatings of the particles.
Okay, because you'll get drastically different results with an angularized kind of simulant versus...
Yeah. So that we are physicists, so in that sense we are interested in all the microscopic properties impacting our macroscopic behavior.
Okay.
Yeah? So that's the goal, and since we cannot try out everything, you have two ways of operating on the moon. You have better modeling, that's what we do partly here, and you saw that we have tons of diagnostics here. So these are the two ways that are a more moderate effort in handling things. You model better, then you're safer, you have a de-risking of what you're doing, and you have a diagnosis on board, and you see precursors of what's happening in your results.
We have time for just a quick second question. Yes.
Yeah, Mateo Rejón, also from DLR. My question is specifically for the experiments of the angular reports. If you have any thoughts on how the lunar vacuum would impact the result that you got from the lunar G flight.
So you are asking about the impact of vacuum?
Yeah, exactly.
Okay. That's another data point we want to collect on the next flight, because we certainly know that you have a lot of trapped air in there. We tried that out, and I didn't show that data because the vacuum was a problem to sustain in that environment. We certainly know all beautiful fountain effects if you have vacuum or not, and that's one of the things that's missing in the modeling typically. So we want to specifically address that in the next flight. So the flight takes place in 27, somewhere in May. We may be back with the results in 28.
Thank you.
Okay, thank you. Let's thank the speaker again. So next up is Karol Seweryn from the Space Research Center of the Polish Academy of Sciences. And we're waiting for the slides to come up. There you go.
Okay. Thank you very much for kind introduction. I will continue the parabolic flight experiment descriptions. Here is a number of people who was involved in my experiment, done in the same flight what Matthias described. Okay, let's go to the next slide. All of us know the let's say environment on the moon. I just want to mention here two projects, or actually three projects, which was a background for us to develop the sampling tool, which are able to, let's say, collect the regolith from the moon surface, and that using this recent ESA parabolic flight campaign, we tested this device against the low gravity influence. So this is a motivation for me, especially the previous flight done on the shuttle, where the experiments was done with different type of soils, and also the change of the density in the lunar regolith, which let's say which is increasing from 1.4 to 1.3 on the surface up to 1.8, 1.9 on the bottom, and the fact that the lunar, let's say, regolith has a very wide particle size distribution. And a few years ago, okay, this is just our experience with the previous devices, but maybe not very important. And in a few years ago, we got a project from ESA to develop the tool. So our aim was to develop the tool to collect the soil and to be able to, let's say, reach around 30 centimeter below the depth using multiple acquisition of the soil. And we wanted to collect around 100 up to 300 grams of regolith per single acquisition. We wanted to have a low impact on the lander or on the deployment, and also very simple and miniaturized solution. So at the end of the story, we have the engineering model of the sampling tool for the lunar environment, which is less than 2 kilograms and with the less than 10 watts power consumption. And we validated this device in TVAC, vibration, all, let's say, tests necessary to reach the TRL6. And these results was already described on the previous conferences, but on that one, I just want to show you the movie, how we've done the test on the, let's say, in the laboratory conditions. So in the laboratory condition, we place the RCE on the manipulator arm, and we just dig up to the 30 centimeter below the surface in the lunar regolith simulant, which is geotechnically, let's say, representative. And after 25 acquisition, we reach the depth, and also we collect around 7 kilograms of the regolith in that time. And what was really interesting for me during last year was the development or preparation of this device for the parabolic flight operated by Novaspace. And we developed actually two racks. One of them is presented here. It's, here is the RCE, which is mounted inside the drum. And the whole big device is just to reset the mechanical regolith properties after each parabola. So after each parabola, we reset the regolith, and we performing the acquisition of the soil in the regolith. So we have the container on the bottom with around 5 kilograms of the different regolith. At each day of the flight, we have different regolith, and one of them was with markers, just to have a chance to do PIV using the camera inside the drum. Here is the movie. So you may, okay, there should be no noise, but I forgot to mute it. You see how it looks like. There are two different experiments with the AGK analog in the low G. Here you have the plot with the torque. This is raw data measured by the torque sensor on the interface. And this is just to compare. One of the experiments was done close to the wall, another not, just to have a chance to do the PIV in post-processing. Today I just want to show you this graph. This is the comparison of the torque on the interface for, let's say, 4 different experiments, 2 of them in the lunar gravity, 2 of them in the terrestrial gravity. The difference is that we have the maximum or minimum density, and in that case, this is the maximum depth of cut. So we just done the experiment with the maximum possible depth of cut for this device. And what you see is a real difference of the, let's say, real impact of the gravity in case where we have really maximum density. So the regolith is packed before the experiment, and we observe that more or less 30% less torque is needed to, let's say, to realize the digging operation. In the same experimental package, we have the second track where we done 2 additional experiments to characterize the soil. So we had the blade cutting experiment to observe the shear properties of the regolith, and similarly to my colleague, a rotary drum experiment to measure the angle of repose. So my colleague prepared some initial, let's say, plots, but it is still not published, showing the vector plot of the, or the velocity vector plot of the movement of the regolith in the low G, and also the initial post-processing of the, let's say, of the angles and its dependence on the drum speed. And also the presentation of the angle of repose versus the gravity level in the, during the flight. I just want to also mention about 2 things, that we are working on the data interpretation. We have the modified Mori-Ishigami model. It is the phenomenological model which, let's say, which cover the shape of the tool which we are using in the sampling operation. And also we are working on the DEM model calibration using the data which we collect during the flight. At the end of the story, I had a chance to, let's say, lead the nice, let's say, team. We somehow give a chance or give an experience for 6 operators. Each day there was 2 different operators from our institute, but also from the AGH, University of Science and Technology in Krakow, and from companies cooperating with us. And at the end of the story, I hope that this, let's say, lesson learned will be used in the future Argonaut mission. And I can imagine, this is my idea of the experiment, that we should not only, let's say, do the sampling operation and, let's say, go with the depth, but we should move this regolith to the container in the moon surface and to, let's say, to record the data from that container. Simply speaking, I would like to have much more data than only the data from the interface. Okay, and with this slide, I would like to thank you for your audience, and thank you for the sponsors, means the European Space Agency and also the National Science Center in Poland.
Thank you. Do we have questions? There's one question.
Yeah, hi, thanks for the presentation. I'm Moritz Pich from OHB. In your data you showed, you said you had a maximum density and a minimum density of the regolith bed for your excavation tests. Did I understand this correctly? I didn't fully get this, sorry.
Yeah, the data is, let's say, under post-processing and will be published, but what I can say, the minimum means the density on the surface, which was around 1.5 gram per cubic centimeter, and the maximum was something which Apollo recorded on the 30 centimeter depth, so it is like 1.8 gram per cubic centimeter. So this density really played a role, not only on the torque, but also, which is not presented here, on the, let's say, power consumption.
Yeah, thank you. If I may ask a follow-up question, so I guess you just compressed the regolith bed to achieve the density? Okay.
Yeah, we had a kind of a stump on the opposite side of the RCE in the drum, and we, let's say, used the vibrator and the stump to compress before each parabola.
Okay.
To appropriate density level.
Okay. And did you see any effects of pre-consolidation due to the hypergravity phase?
This is something which you are not the first person to ask me that question. We are analyzing the video. So for sure, we are seeing the compression effect after the sampling. So let's say once the sample is taken, we observing that the regolith is, let's say, go down. after, let's say, in some sense, losing or after, maybe not losing, but after moving the regolith. This is for sure. But let's say before the sampling operation, we are still post-processing the data. So I cannot answer with good uncertainty.
Okay. Yeah, thanks for the answers. Very interesting results.
Thank you very much.
Any other questions?
Hello. I was wondering if you have measured the statistical representativeness of the sampling method, and if you have.
At the end of the story, we've done 54 experiments using 3 days with the same density, with the same depth of cut. We've done more or less 3 attempts. So the statistics will be not perfect, but I decided to have, let's say, to check different options rather than to have, let's say, good statistics, which maybe could be, let's say, analyzed in the future flight.
Thank you. Very quick one, Matthias.
So when you... Matthias Sperl, previous speaker. When you have a chance to fly again, what would you rather do? Fly lunar gravity again with different compositions of your parameters, or maybe something between 1/6 and 1G?
Okay, this is a good question. This is a good question and hard question. We are, let's say, analyzing what we could do in the let's say next flight. I'm not fully sure if we apply or not. I believe that since this density is important, I would like to somehow investigate it more in details. This density impact during the sampling operation. On the other hand, I would like to have, let's say, more statistics, as colleagues mentioned. So, yeah. There is also an issue that Argonaut is aiming for the South Pole. So let's say the regolith might be slightly different at that place. So this is also an option.
So many unknowns. Thank you very much.
Thank you.
And our next speaker is Xiaochen Zhang from the European Space Resources Innovation Center, ESRIC. And there you go. Is this the
title slide, please.
Yeah. Is that the title slide?
No.
Just the title missing? Is it just the title missing? Or?
No, I think earlier I asked him to check.
That looks better.
Yes. Great, thank you very much. And so to continue with low gravity testing, we're going to talk about our experiment on testing a continuous lunar regolith particle size classification system. And I introduced this last year as well if you attended, but this is a very simple kind of principle to separate particles on a rotating cone. So we feed particles in the stream onto this cone that is spinning at a given speed. And when particles travel down the cone slope, the separation will occur from the friction between the particle and the cone surface. So in general, coarser particles experience less friction or resistance, so they leave the cone earlier and also go a little bit farther from the cone, while finer particles, they have higher friction or resistance, so they get dragged along the cone rotation for a little bit longer, eventually leaving and also settle closer to the cone. And this is adapted from 2 previous studies. And knowing this basic kind of principle, we developed a mathematical model to see that if we have a single particle just traveling on a rotating cone, from the beginning of the motion on the cone until leaving the cone and also eventually landing on this bottom collection surface, what forces apply on it, and how do we calculate the velocity, and how do we predict or calculate where it's going to land. So we did some force balance analysis. We found, there's gravity, there's centrifugal force, normal force, friction, Coriolis force applying on the particle, and also from, and eventually we get this velocity value as well. And from all of these factors, we identified that, all things that are in the red boxes are somewhat related to gravity, which means gravity is a dominant factor that will affect the particle trajectory. So if we run this on Earth and we find it kind of works, how will it work? Will it work in lunar gravity, and can we still calculate or predict where the particles are going to land? So we did a plotting exercise using our mathematical model, and this is, let's say, assuming a cone of 15 centimeters in diameter, which is in the black circle, and I release a particle from the yellow start position, and did my microphone die? Okay, and my cone rotates counterclockwise. Here, okay, thank you. Here I have 6 theoretical or example particles, and I don't use particle size here, but rather I assign a coefficient of the effective friction, because that is essentially what drives the separation. So a particle with a lower coefficient means it's coarser, and the higher coefficient means it's finer. And if we compare both Earth and Moon gravity, in both cases we see that the particle with the lowest coefficient, which means they're the biggest, settle down first, followed by the gradually finer sizes. But in lunar gravity, now running the cone at the same RPM, we see that all the particles, traveled longer in this angular direction around the cone, and also slightly farther away from the cone. So we identified this this trend, this effect in this condition, and we wanted to use this to design an experiment for low gravity testing. So before that, we set up a baseline experiment, a series of baseline experiments in our lab. And for now, we only evaluate the separation outcome mixing 2 sizes from a simulant. And we only test the angular distance separation around the cone, so not away from the cone. We use the same cone size as I used in the calculation before, and for the material, we sipped some LHS1 simulant. We picked 2 sizes, one on the coarser side and one on the finer side, and we mixed them equally in mass ratio. We did test 80 RPM, which is what I used for my calculation earlier, and also we tested the cone running at 30 and 50 RPM. And we evaluate the results of the particles collected within the first 60 degrees from the feeding line. And we see that so with the changing of the cone speed, we see some changes in the overall and also individual fractions collected in this first 60 degrees. But in any case, we do see that the coarser fraction, which is the blue here, get collected more in this first 60 degrees, more than the finer fraction. And if there is a mass percentage difference, that indicates we do have a separation. And of course, the bigger this difference, the better the separation outcome is. So earlier from my calculation, I saw that most of my particles traveled about 20, 25, 28 degrees more than Earth. So we rounded up to 30, and we made a prediction that if I want to achieve this kind of separation result on 80 RPM, we'll need to move the separation line from 60 to 90 degrees in lunar gravity. So, surprise, we were on the same parabolic flight as the previous 2 speakers. We designed our own testing equipment in the form of a stack. We had 3 copies on the flat in two experiment racks. The first rack contained 2 copies, which we call Module 1 and Module 2, and we have a Module 3 in a separate rack in a vacuum chamber. And here I'm only showing the cone and collection part of the whole stack. We do have a poster outside. Some of you already saw that last night, and also we have a tech demonstration later today where we can show you the whole setup. But here for the cone in the center, underneath we have 2 funnels in different sizes to collect and separate the particles. And we do use a vibratory feeder to feed our feedstock, and also, so assuming the end of the feeder is 0 degrees, we have in module 1 the first funnel spanning at 60 degrees, so that's going to mirror our Earth setup, and we can compare how this performed in lunar gravity. In module 2, we have the same kind of setup, but our first funnel is 90 degrees, so that will reflect our predicted results. So we evaluated the particles collected in this smaller funnel and see if our prediction was validated in the lunar gravity. And by the way, for the vibratory feeder part, my colleague Jarrett will be talking about that later in the session, so stay tuned as well. Before testing the mixed 2 fractions, which is the same size we used on Earth, we actually tested them separately and to see if we can get any hints of how particle trajectory differs between the 2 particle sizes. And here it is. I think the result is very clear that the coarser fraction under the same cone same cone speed, the coarser fractions mostly fell within this 90-degree division, and the finer ones mostly went beyond this line. So this is a really good sign that validates the very, very basic concept that particles of different sizes travel in different trajectories. And when we mix them in equal masses again, this is also on 80 RPM, but I slowed it down a little bit, if it plays. You can still see that the coarser particles most went into this first 90 degrees. The finer ones, it's not very clear from the video here, but it did also still move mostly beyond the 90 degrees. And let's look at some numbers. So this is what I had earlier from my lab experiment within the 60 degrees. This is how much of the total mass I've collected and the individual fractions. In lunar gravity, in our first module with the same 60-degree division, I collected less particles compared to the lab. And in fact, we saw a more than 10% decrease in both the total and the individual fractions. For the 90-degree division, we saw a slight increase compared to Earth, but this is still within our expected range that particles traveled an additional 20 to 30 degrees. So this is only part of our experiments on board, but I hope that for now it's kind of clear for you that in this conical particle separation system, the particle friction will drive the separation outcome. And we did some lab experiments and mathematical modeling to predict what is going to happen in lunar gravity, which our experiments so far did support what we had predicted. And of course, there is a lot more parameters we can test to see how they affect the separation outcome. So we are continuing with laboratory experiments to improve our mathematical model as well and perform sensitivity analysis, and hopefully we can find some good options to optimize our system. So thank you very much. Please do come to our text demo session later if you have time, or find us to talk about the whole experience and the engineering setup. So thank you.
Thank you. Are there any questions from the audience? In the back and in the front. Let's take him first.
Hi. Josh Rosero, Xiaochen, hi.
Oh,
over
hi.
here. Space RS. I noticed in the plot that you showed with the different masses collected that you had actually much tighter confidence intervals on your 60-degree separation collector rather than the 90-degree one. Do you have any idea why that would be?
Can you say that again? The comparison?
The slide, one back, one more.
Yes.
Yeah, this one. So the error bars, the confidence intervals on your data are much closer together for the one that shouldn't have worked as well. Do you have an idea why they're wider on the 90-degree one?
I think it depends on how. I think maybe the vibration in the flight does have an impact on it. And for this one, I don't remember clearly, but I think we had some. I think one or two of our collected samples had some deviation. I don't really know exactly what the reason is, but I think for parabolic flight experiments, it's kind of likely that will happen. But of course, I think our engineering design could be improved to avoid this kind of errors in the future. Yeah.
Okay.
Lorenzo Di Mattia from Politecnico di Milano.
Yes.
Extremely interesting presentation. Thank you. As somebody pointed out earlier in the previous poster session, regolith can be extremely abrasive.
Yeah.
Are you planning on furthering the research on how this interaction between the rotation machinery and the regolith affect the effectiveness of this process on the long term?
I think right now this flight is like the baby step of validating the most fundamental separation concept, and most of our setup here is 3D printed. So of course, I think in reality this is not going to be the best material. So yes, we would like to continue this kind of research and to add more kind of regolith properties and choose better materials to test with. So yes, there's a lot more potential after this.
Okay, thank you. Quick follow-up.
Yep.
Also in terms of the amount of regolith that you can process, are you also planning on working on larger scales than the one that you've been working on right now?
Yes, in the reference study, I believe the first one in our reference, they did process, I think, more than 10 kilos per hour or something like that. For parabolic flight, unfortunately, we only had about 20 seconds each parabola to test this, but I think it is very likely to operate this kind of system continuously to process large quantities. Oh.
Thank you very much.
Thank you.
One further question, yes, please.
Thanks, Dave Cullen, Cranford University. Assuming this is done in 1 atmosphere, what's the effect of atmospheric drag on the particles and that contribution to the separation?
So we do have a vacuum chamber test as well, but for that one is more for the functionality check of their equipment more than the science. So right now I can't give you concrete answers, but in one of the reference studies they did also vacuum testing on Earth though, and I think they mentioned I think their finest fraction is less than 75 microns, and they reported a lot of mass loss in vacuum. So that's all I know for now.
Okay, thanks.
With respect to materials, I have a burning question.
Oh, okay.
How do you avoid triboelectric charging? Is there any means of grounding the setup that you're using?
Right now we used a very, very simple way. We printed the cone with anti-static ABS material, but I think it is eventually inevitable to think about how particle charge will affect the separation, because we already see that in this picture that some particles do stick on the cone afterwards, so it's something to be considered for sure.
All right, great. I think any further questions have to wait until the coffee break. Thank you again.
Thank you.
And our next speaker is Miguel Albino from the Imperial College. There he is.
So, can you hear me? Okay, great.
Waiting for the slides there.
Okay, good morning, everyone. My name is Miguel Albino, and I'm from the Técnico in Lisbon, but I worked with Imperial College. My work is about modeling, so computer modeling of the dry particle size classification, so a similar theme to the previous speaker. And I'm a mining and geological engineer. So, where do I point this? Okay. So, yeah. So size classification. It is a crucial step to basically add value and even protect your mineral processing circuit so that a larger particle that basically can devalue the process itself or even break the machine. In current mining technologies, where I come from, two of these technologies can be big screens or even hydrocyclones. However, they are unfit for the lunar environment. They require constant maintenance, they rely on consumables, and usually require very big quantities of water. So they are basically unfit, and we need to find new and better solutions adapted to the environment that we are working on. So one hypothesis, and the one I'm testing, is the use of the Brazil net effect, which is also called vibrational segregation. So basically, you apply vibrational forces, so vibrations, to a particle mixture inside a container, and the large particles migrate upwards, and the smaller particles migrate downwards. This happens because there are two main mechanisms at play. So percolation, where the large particle ascends and the smaller ones fill the void, and convection, that the vibrations create the fluidization of the particle bed, and therefore it prompts convection currents that drag all particles upwards, but the larger particles cannot go down, and therefore they are stuck at the top. Another crucial equation to my project was this dimensionless acceleration equation, which states that the sample is projected upwards and therefore segregates at gamma superior to 1. So basically, BNE solves most of the issues that I presented before. It is not a mechanically complex process to achieve. It does not use water, and it does not require consumables. So at the get-go, we have at least some good things to go for. For the study itself, we structured our research, and we are structuring our research in steps. So the first step is basically understanding how lunar BNE works, so if it even works for lunar gravity. Then we optimize it, and with that information, we inform the decisions that will make the development of a BNE classification system. This happens because BNE is not well understood as a mechanical phenomenon, and it's actually very common in industry and nature, so it's also interesting to understand for other areas of knowledge. I started with my master's thesis, and it was basically about understanding lunar BNE. So for the DEM modeling, we had mainly 4 phases. We had to create a larger container than the one we used in validation experiments, so that the particles would be created in suspension. We allowed them to fall and rest at a stable position. We vibrated the container for 10 seconds, and then we allowed the particles to rest so that we could record their final positions. For the first set of tests, we used the 2 gravity values because we wanted, and that's what I want to highlight, we used 2 gravity values so that we could compare lunar BNE to the terrestrial one and see if lunar BNE worked and if it was better than terrestrial. Our results were actually very promising and are corroborated by the math and the equation I've shown before. So the lunar gravity is more efficient than terrestrial gravity at performing the size classification, and that is corroborated because the gravity renders the equation or creates basically changes the value of the gamma to a point where it doesn't segregate, so it's below 1. So lunar BNE is more efficient, at least in simulations, and we hope to test it in practical settings as well. So basically, for further tests, we needed a KPI to assess segregation. Since we are doing simulations, we can control the positions of the particles, so we use the averages of each size fraction, the larger one and the smaller one, to basically see if they were close. So if they are close, the particles are basically mixed, and this is the scenario on the right. And if they are segregating, the centers of the averages basically move upwards and downwards. So we can not only see if the particles are segregating, but how well they are segregating. And basically this prompted the second test, which was about using different frequencies. So the first test used mostly amplitude changes, and then we tested frequencies with 2 amplitude values to see if that would change something. So what we saw was that up to some values of frequency, as they were increasing over time, so over the 10 seconds, the larger particles, which are the red lines, and the smaller ones were diverging, so therefore they were segregating. And if the frequency increased, the segregation was faster and more efficient. But there was a point where the frequencies were so high that the container moved so fast that the segregation started decreasing. And therefore, we found that probably there would be an optimal value, an optimal pairing of amplitude and frequency that would prompt optimal segregation. So that's where the research diverged to optimization. So the first results that we got from the thesis basically had two points and an initial relationship that basically established an inverse relationship between amplitude and frequency. But in reality, we are having the points are too far apart so that we could tell the maximum is actually here or how actually the phenomenon works. So we needed more data. And that's basically what prompted the optimization of the BNE. So now we are back to using Moon and Earth gravity because eventually we want to test another parameter, which is the gravity change. And we are using many amplitude values and very small differences in frequency to capture that maximum as well as we can. So one of the examples that we are using here, it was actually an Earth test. You can see the exact point that the particles start segregating quite well, and you can even pinpoint a maximum point. With that point, we move that to another plot, and we use that plot to make a line, basically stating that that line would be the optimal segregation line for every frequency and amplitude combination. One other thing is that that maximum is not, it captures like an interval between the seeds, and therefore we have an optimal interval of operation instead of a defined maximum. For industry, that's really quite useful because you don't have the value that you need to get every time. You have an optimal interval that you can get very good segregation behavior, and therefore for industry that can capture some errors that might occur. So basically, these are the results. These are very early stage results. So we obtained those optimal segregation curves, and now we can do the inverse. So we can just define a frequency that we need for a parameter that we have, and we can basically calculate the amplitude that is necessary to obtain optimal segregation. And therefore, you can basically use this for two cases. If what you want to do benefits from BNE, you can find that value within the curve. And if you want to avoid it, you basically have to avoid that curve. So for final remarks, basically lunar gravity conditions benefit the Brazil net effect, which is very, very good since that's what we are studying. The results suggest optimal points, and those optimal points suggest combinations of amplitude and frequency that produce optimal segregation. And the latest simulations suggest that these points are actually intervals and therefore are good for basically producing industrial systems. For future work, since we are trying optimization, the approach that we are taking is learning slowly how to make BNE work. So we are introducing new variables to this optimization study so that we know how the curves change, how the behavior changes for optimality. So we add gravity, we add particle size distribution, a larger particle to container ratio to accommodate larger sizes because we had very few particles and very few quantities. Obviously, those lines, and since I talked about intervals of operation, these need to be added to the plots so that they are actually usable for industrial purposes. And we will use, as I said, that information to build a continuous BNE classification system. But the project that I want to do for a PhD will try to integrate that BNE classification system to do something with it, to have a target of classification so that basically we can tune and cross-develop the system with the needs of a downstream technology. So yeah, that was my presentation. I hope you liked, and I'm open for questions or to talk later.
Thank you, Miguel. Matthias. Oh.
Matthias Sperl, DLR in Cologne. How confident are you that if you replicate your experiment on the next parabolic flight, that it will turn out exactly as you simulated?
So my expectation on...
Yeah, so what are the unknowns?
What are the unknowns? So I think the biggest one, since we are trying to segregate lunar regolith, is the change of the particle medium. We are using spheres for this. We used spheres for this study, which are very good shapes and produce very simple results. But once we introduce angularity, complexity, the friction changes, and therefore the BNE, in my opinion, will basically take longer to occur. So I hope that basically this is very early stage, and we just tested 2 variables, amplitude and frequency. So we need, I think, before a parabolic flight, we need to test at least some other variables and not have such a small container so that it can be at least viable to test and to have an experiment that produces interesting results.
Okay.
Hi, thank you for the presentation. Taya Birch, representing the ROXY and UPREB projects from Airbus Defence and Space. Very interesting presentation. I'm curious, it goes into the direction of your previous answer. For your simulations, you're using spherical particles. I was wondering how you expect the morphology of the particles to influence the segregation.
So, as I said, I think that it will add a lot of friction into the system. It will most surely require more time to segregate efficiently. Actually having a complete particle size distribution will also add the effects. Some papers actually state that it becomes complicated to segregate material when you add a complete particle size distribution. But yeah, that's why we are doing research.
Thank you.
Time for a quick last one.
Hi, Bupe, with Polymac. I just wanted to find out what DEM software were you guys using, and if you went on to do any physical experiment for the BME, and then how are you accounting for the coefficient of restitution for the particles?
Okay, so first the DEM model that we used was YADE, which basically was chosen because it was free. Since it is a master's project, we don't have money. So about the physical, so the second part of the question was regarding the coefficient of restitution within the tests and the experimental validation, right? Okay. So the coefficient of restitution, the particles that we used in the experimental validation, so we calibrated the model. I didn't have time to show that, but before doing all these simulations, the first ones were actually to calibrate the model to physical reality. So we used actual experiments, we used simulations, and tried to fit the simulations with the experiments so that they would at least reproduce terrestrial gravity, and then and only after that we transported the physics to the moon. So the coefficient of restitution used was the one of basically the information of the provider of the glass beads. And yeah, we used experimental validation for the tests.
Thank you.
Thank you.
Okay, our next speaker is Jarrett Dillenburger from the ESRIC again.
I'd say it's nice to see you all, but I can't actually really see you all at all. It's quite bright. Okay, so for the last 60 years or so, we have viewed lunar regolith as a bit of a liability. It's sharp, it's got a lot of these agglutinates in it, it's very angular, and it's very fine. And so this is a nightmare for Apollo-era equipment and for more recent equipment on the moon. But I was wondering if it's possible that these nightmare traits that cause it to be so difficult to work with could actually be an advantage, could have a benefit when we're moving this material, when we're moving the regolith around on the lunar surface. So today I'm going to be talking with you about a technology that we tested in lunar gravity, vibratory conveyance, which allows us to understand a little bit more about how we can move these materials. So when we look at the ISRU flow sheet, one of the things that stands out in the early part of this is that a lot of the aspects inside of beneficiation and even in extraction, we'll highlight it in orange here, all of these are relevant at every scale for regolith transport. So we have to move the materials from point A to point B, both inside of different modules, inside of different units, as well as between different units, so beneficiation unit to, say, an extraction unit. And so Because this is a problem at every single scale, it's relevant on the most upcoming missions, as well as missions that may happen in 50 years. And solving this problem is then really important. The problem that I've identified is that the short-range transport, so moving it in between these units, is still an open question. We don't have a definitive solution for how we want to do this. And it represents a critical bottleneck in our ISRU operations. Now, my solution, the one I'm biased towards, is vibratory transport. As a brief overview for the vibratory transport that we were testing in lunar gravity, it's essentially, we have an oscillating surface that lofts the particle ballistically to achieve net transport. And so in this way, we provide an efficient way to move particles forward in one direction. Now, some of the advantages here over potentially other systems include the fact that it's low power. It also has very few moving parts aside from the vibrating surface itself, so we can use a single actuator in some cases to move these materials. It also has an enclosable flow path, so when you're moving dusty regolith around, you can actually entirely enclose that regolith inside of a tube or some other equipment to ensure that you're not producing lots of dust in that process of moving it, keeping your equipment clean, and reducing the chances of having mechanical issues down the line. Finally, it's omnivorous, so it can take a lot of different materials, different sizes, both for raw lunar regolith as well as for beneficiated regolith. And finally, it can even handle materials that come out of a reactor. So the different types of slag and mixed metal alloys that you have can also be moved using this type of technology. However, in all of this, one of the big knowledge gaps is that we haven't actually tested this technology in lunar gravity at all, at least to my knowledge. And so this became a really important aspect of figuring out, will this system perform in lunar gravity? Will it perform in vacuum? So to test this in lunar gravity, we had three major questions. And as my colleague Xiaochen mentioned, this was part of the larger payload that we did as part of ESRIC on one of our flights. And so these major questions, the first is simple, and that's how does the gravity affect the ability for these particles to move? The second one was how does the size impact that, so smaller particles versus larger particles. We had 4 size fractions. 3 of them were unimodal, and then 1 that was bimodal, so this was a mixture of 2 of the other ones. And finally, we were interested in understanding how the agglutinated materials, so these very angular glassy particles, performed in comparison to angular but less angular standard lunar regolith simulants. Now, for clarity, all of these experiments are performed under identical vibration parameters, and they were done under ambient atmosphere for the experiments that I'll show today. We also performed them under vacuum, but I won't be revealing that information just yet. So in order to actually perform these experiments, this is one component that was on our payload, and it's essentially a unibody printed, 3D printed transport trough. I'll let you see from the top view as well, and also a cross section. And so in this case, our powders go into a loading chamber. They're then conveyed through the transport channel, and they come out at the end and go onto a cone, as you saw earlier. But we have a single camera that's monitoring the movement of these powders across the surface. Now, what we know from, so I'll show some data here. What we know is that in lunar gravity, we expect that these materials should travel further for each hop that they take. This was supported, of course, by previous DEM simulations from Kawamoto in 2022, where they also showed, highlighted in orange here, that the calculated speed should increase. In our experiments, I have some fun videos for you. We see exactly that. Perhaps. There we are. So in lunar gravity, the powders are moving much quicker than they are in Earth gravity. This should repeat. And so this is just for one particle size. This is all LHS-1 materials. But what we're also interested in how is the sizes themselves are impacting this. So looking at the different particle size ranges in here, we noticed that there was something quite interesting happening, and that is that there's an inverse relationship between the particle size and its actual transport speed. And so this is quite interesting that if you're beneficiating material and you've now separated them out into different size fraction streams, if you're using a vibratory system, it's possible that they will actually move at different speeds. We need to adjust for that when we're designing our systems. The other aspect of this that we're really interested in was understanding how agglutinates affect this. Now, agglutinates make about 40 to 60% of the lunar highlands regolith, so it's very relevant for understanding how these materials will impact and how their dynamics will be affected moving in the vibratory feeder. So we were just using lunar simulants. This is an example of what they kind of look like, so an optical image. And we also had two other simulants, so the LHS1 and OPR-H2N, as a comparison for less angular materials. And what we find here is really quite fascinating. In fact, the LHS1 and the OPR-H2N, so these non-agglutinated simulants, had an elevated but the same approximate transport speed. But in fact, the agglutinates, we'll see here in the video, move much quicker. And so this suggests to us that agglutinates, these more angular particles, may actually perform better from our experience in lunar gravity than a typical non-agglutinated material. So this leads us to essentially three major results, and it's what I want to leave you with today. The first is that lunar gravity is an enabler for this technology. So vibratory conveyance increases the transport speed, our ability to move materials around, so that increases the efficiency of the system, and gives us an ability to use less energy to move particles in the lunar environment. It's also important to note that size matters here, right? So we see that different sizes lead to different transport speeds that come out. And so that plays an important role for the type of materials that we're moving through. And finally, the agglutinates appear to be faster, and so knowing that, and because they're very relevant for, let's say, lunar highlands environments, we may be actually able to use that, something that is, as I said, a liability, may actually be a performance asset. The last 2 points I'll leave you all to think with today is the idea that the studies that we do here terrestrially are really important, but the results show that they're probably underestimating the actual performance and the ability of these types of technologies. And finally, that this type of technology, lunar transport, can be used as a lighter, lower power, and potentially more capable than terrestrial analog systems that we have been testing here on Earth. Thank you so much, and happy to take questions.
Thank you, very interesting. There is an immediate question.
So, Jerry Sanders, Esric, have you thought about looking at a vertical transport? I know NASA had a experiment on the Blue Origin mission, but it failed to turn on for that, so we missed those data points. But do you see yourself going, some kind of a spiral vibratory or inclined?
So that's a great question. Yeah, I think it was Aaron Olson and his team there with this one. Yes, I think vibratory transport vertically is really important. I have looked at a couple of different tests under vacuum just terrestrially with the spiral elevators. And vertically is also interesting. Kawamoto has done some work with that as well. But I think I won't reveal it all today, but there's actually another way we can use vibrations to move them vertically. We saw some earlier results as well. So there are a couple of really good options that are waiting for us. Yeah.
Well, we'll talk offline.
I look forward to that.
There's another question.
Hi, it's Vivek.
Am I too close?
Do you think whether cohesion can impact this technology, the cohesion between the particles?
Yeah, I think the answer is absolutely, to make it short. This is something that we're going to be studying more in depth with future lunar gravity flights. But it becomes something that's much more of a problem under vacuum than just in air like some of these experiments. So we also performed tests in vacuum, which I haven't showed the results today, but I will tell you that excitingly they do work, and we can move materials in there. So cohesion.
Do you observe lumps, or still you are getting a spontaneous, reliable flow?
Yeah, so you get a reliable flow, absolutely. The clumps, for the most part, are, I don't want to use the word destroyed, but they're broken apart because of the vibrations. And so it depends on the vibration parameters. But yeah, you can definitely remove some of the cohesive effects of the powder under vacuum in lunar gravity just from that.
Hello, Venu from International Space University. So my question was, the channel that is carrying the regolith, can that be damaged a little faster because of the vibrations? And if so, like, is there any solution towards it?
Yeah, it's a good question. So there are always trade-offs in everything we do. And in this case, if you pick the right frequencies, so you avoid sometimes, if you can avoid resonance frequencies that could potentially damage, you can avoid some of that. And there are also a lot of engineering methods that can be used to mitigate the effects of vibrations. But it's certainly something that has to be considered, right? If you have a system that's shaking a bunch, it needs to be secured in a way that doesn't cause the system to fall apart.
Oh, Matthias Sperl, DLR in Cologne. On your previous slide, you conclude that you go further if the gravity level is lower.
Yes.
When does this end? So if you go on an asteroid, you shoot all the way to Mars?
You know, technically that could be true, but in essence, it has to do with basically the amount of interaction that the particles have with the surface. So if you have very low gravity and you throw them, they just continue, and you lose out on the opportunity to essentially to control them within that environment. So if you're on an asteroid, for example, this type of technology is probably not going to be very relevant. And I think that conclusion has been predicted in other papers as well. Yeah.
There was another question in the back.
Mel Gelderman for Space Age Ventures. So actually on the back of that question, are you able to use the upper side of the tube to basically reflect the particles and actually keep accelerating them faster and faster? And then what is also the maximum incline that in your experiments these particles will move? Thank you.
Yeah, those are both very good questions. So to answer the first one, we did design the system so that we wouldn't have particles contacting the top surface. Intentionally, we just wanted to have bottom contact. But we do imagine if you had a smaller diameter system, you could absolutely use that to your advantage. So they would get an impulse from the top. For the second question, which I've now forgotten, I'm sorry. Oh, the incline, thank you. Yes, terrestrially, you can get, I've gotten about 30 degrees as an incline just in my own testing, but we didn't test that in lunar gravity. So that is an open question.
Okay, yeah, let's have another one.
Hi, Jarrett. I just have a question on your last slide. You mentioned that your system has lower power. I'm assuming this is power consumption. I don't know if you've tried to compare the different systems that are used for transportation on terrestrial applications, and how does your system fare to those systems? And at 30 degrees, what is, I would ask, the throughput of your system?
Yeah, so as far as energy usage goes, what we have found is, maybe this is, I'll say that it doesn't take much energy at all to move kilograms of material in this way, but I haven't directly compared it to other materials. So in our particular case, we're using less than 1 watt for moving all of these materials. But there's still some additional tests to do related to that, for sure. Thank you.
Okay, maybe one last.
Yeah.
Hello, Johan. I'm Johan from Moon Experts. If you already inclined the plate, have you noticed any bristle nut effects coming from that?
So I don't have any definitive evidence to show you, but actually during the flight, when we had mixed samples, there was some evidence of that visually happening. So you could see particles rise, larger particles rising to the surface in some cases. Yep, absolutely.
All right, thank you for these questions and for the talk.
Thank you.
And our last speaker is not Michel Lavagna, it's Sabrina Lanfranco, also from Politecnico? Yes, okay.
Okay, good morning. I'm Sabrina Lanfranco. I'm a PhD student in Politecnico of Milan in the Astro Research Group, and today I'm going to present one of our work that is a miniaturized sampling tool for non-cohesive surface material. Okay, so our main goal was to develop this miniaturized sampling mechanism for the planetary loose soil in order to support the in-situ science for small payloads. This is due to the fact that from the on-surface analysis, we can retrieve extremely important information, obviously, both for the scientific and the technological development. And then, let's say, these small assets multiply mission opportunities, since, for example, a miniaturized sampler can fly as a secondary payload. And these mission-independent tools, let's say, can be reused as in different missions with different targets. So, okay, we target planetary bodies that present a loose material layer on surface. So we don't need the rock fragmentation, but just the material transportation from the surface to a possible analysis chamber. So we want to collect some few grams of material, and everything should be contained inside a 1 unit dimension. So for that, miniaturized, because it should be small and super compact. So the baseline that we adopted is basically to define two different geometries that are complement together. So there is an external drill just to create a stable interface between the soil and the tool, and it basically manage the penetration forces if we need some or few penetration in the soil. And there is this auger conveyor that his functionality is just for the material transportation upwards, so from the surface to this possible analysis chamber. So from this conceptual baseline, we are able to define our research question, that is basically if this miniaturized auger conveyor is suitable for the transportation of the loose granular material. And if it is like that, which are the conditions that can affect these functionalities. So we define them considering the geometry influence, the operational condition, and also the critical boundaries that can lead to instabilities such as the jamming and the fold back of the material itself. So in order to define the best geometry solution, we adopted two different approaches. One is analytical numerical one, starting with the Roberts model in order to retrieve the volumetric flow rate for the material, and from that we retrieve also the geometric parameter for the auger conveyor, so the diameter, the pitch, and the clearance. Then a perforation model in order to define and retrieve the perforation forces and also the torques. And a discrete element method that is right now under development in order to run simulation for a better understanding of the interaction between the tool and the soil. The other part is an experimental approach in which we test this auger conveyor geometry in order to, let's say, compare different geometry configuration and also different operational condition. And the outcome of this experimental test will be used, let's say, to calibrate and to validate also the discrete element method. In fact, as I said, this is under development. Let's say we run simulation on the engine environment that consider the contribution of three different models. The mechanical one that was already developed inside the engine. We just added the contribution of the thermal and the electrostatic part. So our objective is to validate this model so that we can run simulation also considering different environment conditions such as low gravity environment. Okay, so moving to the experimental campaign. This was set up for testing these different geometry combination of the parameters that we can retrieve from the Roberts model, such as the screw diameter, the pitch, and the clearance, but also the draft depth, that is the offset between the internal screw and this external cylindrical container. So what we done also is varying the operational conditions. so different penetrational depth, different inclination at 0 degree, 15 degree, and also 30 degrees, and also different angular velocity. In order to define which, let's say, geometry is suitable or best suitable for the transportation of the material, we obviously compare the output of the experiment, like the mechanical torque, the mechanical power, the soil transported mass, and also the specific energy. So we identified 6 different geometries, as you can see in the photo, from G1 to G6. They are 7 centimeter long, so they are super small, and 3D printed right now. What we've done, so the test bench was done in the Astra Lab at Polyme, and it is composed of this auger conveyor, then obviously an external cylindrical container made of glass, just to we can see through it during the experiment, and a stepper motor with controller and an encoder. For what concerns the Regolith sampler, we use the carbonaceous chondrite Chi asteroids. So we run almost right now 60 simulation, 60 tests, different tests, and we end up at the results that no matter, let's say, the type of geometry and the 2 different, let's say, velocity that we use, but if the tool is not inclined, we cannot collect material from that. So that means that the poor rotational velocity is not sufficient. We need inclination because it better help us to engage material inside the tool. Then this engaging material is also triggered by the draft depth, as I said before. We can see that in the video because if we, I just wanted to rerun the video, okay. If we incline the tool, but the draft depth is not present, also with that we cannot retrieve material from the incline situation. Another let's say, parameter that affects the engagement of the material is the, let's say, ratio between the pitch and the diameter of the geometry. In fact, we compare different geometries with the same diameter but different pitch. So if this ratio is lower, we have a better flow stability. In fact, we can see them in the plots above. So the best results, the best configuration is the G2 geometry using an inclination of 30 degree and 600 RPM as a velocity. Okay, so arriving at a conclusion, we can say that we have qualitative agreement with the analytical numerical model, but not quantitative, let's say, because the Roberts model overestimates the mass flow with respect to what we can see from the experimental part. Analyzing the experimental results, by now we can respond, let's say, we can answer some of the research questions, such as the fact that, yes, there are the geometry affects, obviously, the transportation of the material, specifically the ratio between the pitch and the diameter, but also the ratio between the clearance and the diameter of the particle that should stay inside a specific range that goes between 1.4 to 2. Otherwise, we can see jamming and also the fall down, the fall back of the material itself. For what concerns the operation condition, we can say that the inclination and the draft depth is mandatory. Otherwise, we cannot collect the material. So right now, for the future development, obviously, we have to more further investigate, doing more testing, and also try to validate the discrete element method, because in that way we can also run simulation with that kind of geometry in reduce, let's say, gravity. Okay, thank you for the attention.
Thank you. Questions? 1, 2.
Piotr Kulinowski, AJH University. I have to ask about rotational speed.
Yes.
600 rotation per minute?
Yeah.
It's true?
Yeah.
It's hard to believe. It's too fast.
No, yeah.
Few
It's
times too fast for drilling even.
Yeah, I know, but the fact is that, let's say, it's super short, okay? So we just wanted if we lowered the velocity, we couldn't extract mass, or let's say we could it, but like in minutes of the simulation. So we tried to see if obviously using a velocity that is higher would work in the same way. Right now, yes. Obviously, I don't know if we will use that velocity in situation in which there is a, let's say, reduced gravity. Because if there isn't an anchor system, that obviously could, let's say, pull up the lander from the surface. But right now, yes, 600 rotation per minute.
Yeah, sorry, go ahead.
Hi, Miguel Albino, University of Lisbon. So you use a very small system. What do you expect to happen, especially when you increase the particle-to-system ratio, so the corkscrew mechanism?
Yeah, we already done that using, let's say, because these tests were done with particles that were lower than 1 millimeter. We've already, let's say, done some tests with higher diameter, and obviously it blocks because there is the jamming effect. For that I said that the geometric influence of the ratio between the clearance and the diameter of particle was important, because otherwise particles cannot enter or blocks the system itself. So
Sorry.
No, okay. So obviously it should scale up depending on the type of, as I said, the loose soil material, okay? If we want to collect a certain type of particle with a certain type of diameter, we have to scale the geometry based on that, yes.
My question actually was for the other case, where the system is way bigger and the particles are small.
Yeah, they fall down. System. Yes. Also, we test that case. For that, we retrieve the range in which the geometry, the ratio should stay. They fall down, obviously, because, okay, right now we are in a Earth gravity. So maybe in a zero gravity condition, maybe the particles don't fall down. For that, we want to use the discrete element method also for test that option. Okay, yes.
Thank you.
Mel Gelderman, Space Age Ventures. So I wanted to ask about, in one of your first slides, you showed the combination of it being both a drill and an auger.
Yeah.
And in that situation, would only the outer side rotate and the auger would stay still, or do you need to control both?
Okay, so right now we test only the option in which the external drill, let's say, stay fixed, it doesn't move, and only the internal, let's say, the internal screw move for the transportation. But we want, obviously, to test also all the other possible, let's say, configurations. So both move in the same direction or move in opposite direction. And so we will see the outcome which is better respect to the other.
So it's not possible to have both functionalities with just one moving part? You need to be able to control both?
Yes, exactly, yes.
Okay, that concludes the Q&A. Thank you to you, and thank you to all the speakers of this session. However, before we conclude this session, I have two announcements or other advertisements to make. So, as we saw a lot of excellent experimental studies and model correlations, I invite all the speakers, if you're considering to publish your work in a journal, to look at the SPR, which is Space and Planetary Resources. It's published by Springer, and we're inviting all publications, all manuscripts regarding space resources. So do have a look at this journal. And there's another announcement by my colleague from Japan regarding further microgravity lunar G flights.
Thank you very much, Philip, having me here. Please give me very quick introduction of our brand new service. My name is Munenori Takahashi from Space Quarters in Japan. So we have just started microgravity flights. We can do 16G with a space vacuum chamber. So we can realize the 10 to -5 Pascal orders vacuum conditions with parabolic flights. And we already actually installed our vacuum chamber on the parabolic plane. So you don't need that much time to preparation or the costs itself. Maybe it takes just less than the 200K euro, something like that. Yeah, so, and we are very, we actually work with the Diamond Air Service, which is 100% under Mitsubishi Heavy Industry Corporation. And we are very open to anyone, even the overseas countries or overseas research institutions like you guys. So if you have any interested in using this service, please feel free to reach out me, and also we have our website, so go find the Space Quarters, so there is a contact form. Yeah, so I hope this information is something helpful or interesting for you. Yeah, thank you very much.
Thank you. I think we agree that we need more lunar GE partial G flights in the future, and with that, enjoy your lunch break.